Okay, now I'll share my screen. All right, so we'll get started. So this course is ECE1504. It is statistical learning. So let me just briefly give you the outline of what will be covered in the course first before we go into the first lecture. So the field of machine learning basically involves the study of computational systems that adaptively improve the performance using some data. Okay, this is a very general and broad definition. In this course, we are primarily focusing on statistical learning. And this entails studying theoretical foundations of machine learning. Okay, so we are focusing on the theory side of machine learning. So again, there are many topics to cover based on the instructor's preference and so on. The main topics that we will cover in this course are as follows. We'll first study Pac Learning starting today. Then we will develop information theoretic bounds. For generalization. After that, we will develop some fundamental lower bounds. We'll develop minimax lower bounds. And then we will study graphical models. As the last topic in this course, we'll study both the inference, learning, and so on. Gaussian processes. Okay. So this will be the main topics covered in this course. Now, there are other courses in this department on statistical learning, or not in this department, but in other departments. CSC2532 is one. STA314 is another one. So these are also called statistical learning. They cover very different topics than this course. So the person, an ideal student for this course, the one that ECE1504 is a student who's doing research in the field of communication systems and wants to identify some connections to statistical learning. So somebody who's interested in information theory, communication systems, and wants to see if any of these tools can be applied to statistical learning. So it's a fairly niche sort of topic that are covered in this course. It is not like a basic intro to statistical learning. Some of these other courses might be more worthwhile if you are interested. But this course, at least last year, the way it was developed, and again, I'm continuing this year, is mainly targeted for students who are interested in information theory and communication systems and who want to see how these tools from those fields can be applied to statistical learning. This is something that I am interested in, and that's the focus of this course. It is not like a very general purpose course. So you should take that into account. So the way the structure of the course is going to be, the way the course is going to be delivered this semester is that we have online video lectures. In fact, all the lectures have been posted except the first lecture. So all other week lectures have been posted. So really, we won't have like an online delivery every week. The lectures are already posted. They were actually from last year, previous semester, but it's basically the same content. So you just don't have to pay attention to the dates and so on that are mentioned during the lectures. But I gave those lectures last semester, and they're all video lectures. I have linked them. If you go to the Quarkus webpage, you will see that all the lectures starting week 2 have been posted along with the notes. So you just have to follow the lectures and the notes. And basically that's how you will be able to learn. So we won't do a synchronous learning like today. We will use Piazza to discuss any questions for each week's lecture. So when you view the lecture, you have any questions, you can use the Piazza discussion forum to ask, and me or the TAs, we will answer the questions. And this is how we will develop. I will have, again, every week an office hour, essentially. Mondays at 2 p.m. where we will discuss the contents of that week's lecture. So I won't give a full-fledged lecture. You will be seeing this on video, the video lecture that we have, but I will just basically answer any questions you may have about that week's lecture. That is how we will sort of conduct. You should first ask questions on Piazza and we can answer them. And then during the lecture, we can have further discussions and clarifications. So this will be the structure of the course. In terms of grading, in this semester, there will be participation grades, which is worth 10%. So if you, depending on how active you are on Piazza or during office hours and ask questions, that will count to 10% of your grade. There are 2 problem sets that are already posted along with the due dates, and they are each 20%. And then there is a final project, which is worth 50% of the grade. So this is going to be your grading scheme for this course. We won't have exams this time. It will mostly be a final project, 2 problem sets, and the course participation. So the problem sets will cover the lecture materials, and the final project will be something, a research project that you propose, ideally at the intersection of information theory and machine learning. So I'll pause here and take any questions before we go into the lecture material. So you can unmute your microphone and ask questions, or I guess you can type it in the chat window.
Sorry, Professor. You said that office hour would be Mondays at 2 p.m., but Monday, this is right class, right?
So the lecture slot is 2 to 4 p.m., right? So essentially, we will use it as an office hour because all the videos are posted. So you will be seeing all the videos beforehand for that week at some point. So for week 2, you will have between this Monday to next Monday to see the video, ask any questions on Piazza, we will have them answered, and then we will have a final discussion next Monday at 2 p.m. for next week's lecture. So what I can do is I can do a short summary of the lecture for that week, and then it will just be an open office server where you ask questions.
And which text we need to go, we can find the, is there any textbook for the course?
So the textbook varies, like mostly it's not, there is no single textbook. For the first part, a recommended textbook is Learning from Data by Abu Mustafa. So this is a recommended textbook. I will be taking material from this textbook for the first part of the course. But later on, when we go to information theoretic bounds, it's based on research papers that I will post. Most of the materials here is based on research papers rather than any specific textbook. It is a fairly like cutting edge, like some stuff that happened last year and so on that we will be covering. So it's mainly a course that is designed for people who are experts in information theory and communication systems who wants to understand statistical learning. So there cannot be a single textbook that covers everything.
Professor?
Yeah?
So do we need to have a background in information theory to take this course?
It's helpful, not necessary, but then you will have to do some reading on your own. If you don't have a background, you will have to you will have to basically read up some material on your own in order to catch up. But it's good to have some exposure to information theory. But I don't expect you to take a course. I don't expect you to have taken a course. That's not the point.
Okay.
Any other questions? I don't see any questions on the chat. So we can proceed if there are no further questions. So the Piazza discussion forum has been posted. Okay, what happened here?
Your voice is noisy, Professor.
Oh, my voice is noisy? Let me wear a headset maybe. One second, something. Hello, everyone. Am I still audible? Is it better now, hopefully? Okay, so I didn't hear any complaints at least. So let's get started. Okay, so we'll start with the first topic of the course, which is Pac Learning. So here we will consider the area of supervised machine learning. And we will assume here that X will be used to denote the data vector, and Y will be used to denote the label. So the setting is like this. There is some unknown function that we don't know. There's some unknown function that is used to generate the labels. There's some function f that takes a data vector and generates the label. F is not known, and this is something we want to learn. Also, there is some unknown distribution P of X that is used to sample the data. So we have the unknown function f and the unknown distribution P of X. And these are used to generate the training data set. There is some training data set D, which is of the form x1, y1 up to xn, yn. Okay. And this training set is what we can observe in training a machine learning model. Unknown function f, neither do we know the unknown distribution P of X, but we observe some samples of it. Now the sample points xi are generated IID from the distribution Px, and the labels yi are generated using the unknown function. So each xi is fed into f and yi is generated. So f is like the ground truth that we don't know. Px is a distribution used to sample the training points that we don't know either. However, we see the training set D, and then this goes into a learning algorithm. In the learning algorithm, we feed in a hypothesis class, a hypothesis set. So we have to decide what kind of model we want to train, and that is the hypothesis set. So do we want to restrict to linear models, or do we want to restrict to some high order polynomials, or do we want to restrict to some, say, neural networks? That is what H is. So H and D go into the learning algorithm, and we get an output hypothesis. G, which is an element of H. Okay, so this is sort of the framework of Pac Learning. Now we have two types now of performance metrics. One is the training error. This is also known as the in-sample error. So we want to see how good our output hypothesis is. So the way we do it is we measure what is the error on the training data set D. So E in is given by the summation of I going from 1 to n, little e of yi and g of xi, where e of y and g of x is the error on the data point x comma y. So y is the true label, gx is our prediction, and we want to see whether our prediction matches the true label or not. We will mainly consider classification problems. And in these problems, e of y and gx is 1 if y is not equal to gx. So we make an error if our estimate is not equal to the true label, and it is 0 if y equals gx. So in other words, this is the indicator function that y is not equal to gx. So in classification problems, y is usually some sort of a discrete valued label. If in binary classification, y can only take two values like 0 or 1. Or in multi-class classification, it takes one of finitely many values. G tries to predict the label of x, and if it agrees with the true label, then we say that there is no error. If it does not, then we say that there is an error. So that's why E is a 0-1 function. The other type of error that we will consider is the out of sample error or the test error. The other metric is the test error, or it's also known as out of sample error. Okay. In this case, we assume that we have a fresh sample x that is sampled from the same distribution as px. And then we have y, which is f of x. So y is generated by using the ground truth. X is the true label, or x is a fresh data point that is sampled. And we see how our output hypothesis G performs on this sample. So we compute E of y and gx. Okay? And then we take the expected value with respect to x. And this is known as E out, the test error. Okay? I should mention here that x is independent Although it is sampled from the same distribution P as a training set, it is independent of x1 to xn. So it's a fresh sample. And it is easy to show that for classification, when E of y and gx is the indicator function that y is not equal to gx, E of x, E out is also equal to the probability that y is not equal to g of x. Okay. So in practice, we are interested in having small test error. Like we want to train a machine learning model so it performs well on fresh samples, the unseen data points. So E out, however, is usually the quantity of interest. However, E out cannot be directly measured. As a result, we want to estimate E out via E in, which can be computed. So we can compute E in, but that is the error we make on the training data. That is not so much important to us. What is important is the error we make on fresh samples, the test error. So E out is usually the quantity of interest, but we can generally cannot directly compute it because Px is not known, f of x is not known, and so on. However, we want to estimate it via the quantity that we can measure, which is E in, the training error. So what Pac Learning does is it provides us a mathematical framework to develop a relationship between E in and E out. So in order to understand this, we will do an example. Suppose we have a large jar with many balls in it. Okay, there are some balls that are colored red, other balls that are colored green. So we have a large jar with red and green balls. And our goal is to draw a small sample of balls at random and estimate the fraction of red balls in the jar. This is what we want to do. We want to draw a small number of balls at random after mixing all the balls in the jar and then estimate the fraction of red balls. Okay, so we will define an indicator function z to be 0 or 1. 0 if green ball is drawn, and 1 if a red ball is drawn. So we will define, so z is a Bernoulli random variable. We'll define probability that z equals 1 is mu, and probability z equals 0 is 1 minus mu. So in other words, z is Bernoulli mu. And our goal is to estimate mu, which is not known to us. This is the fraction of red balls in the jar, and this is what we want to estimate. So what we do is we make n independent draws. So we'll let z1, z2 up to zn. These are the n independent draws be the outcome of n independent draws. Okay, so each zi is 1 if red ball is drawn in ith trial or ith draw, and 0 if a green ball is drawn. So probability again zi equals 1 is mu, and of course we assume that z1 to zn are IID Bernoulli mu. Okay, Now what we do is, in order to, we don't know mu, we just observe Z1 to Zn. And what we want to do is we want to compute an average of them. This is what we do. We take the average of the number of red balls, how many times red balls came. So we take the average of Z1, Z2 up to Zn, and we call it Vn. And we use Vn as an estimate of mu. So the idea is, as n becomes large, Vn will become a better and better estimate of mu. So the picture you should have in mind is the following. Let's say this is n, and we sketch Vn as a function of n. And let's say the true value of mu is somewhere here. Then Vn, a sample sequence for Vn may look like this. Based on how we draw, based on the actual random outcome, we may see something like this, for example. The point here is that as n becomes larger and larger, Vn will tend to become closer and closer to mu. So it will become a better and better estimate of mu. Okay. Of course, we can easily show that the expected value of Vn is always equal to mu. For any n, the expected value of Vn is equal to mu. But in practice, we only have one sample sequence. So this is not quite useful. A particular bound that is very useful is the Hofdings bound. It says that if you look at the probability that Vn minus mu is greater than some epsilon, for any epsilon greater than 0, is usually very small. And in fact, Hofdings bound says that it decreases exponentially in n according to this formula, 2e to the minus 2n epsilon square. So remember, Vn is a sum of n IID random variables. And this says that this concentrates very close to mu, in the sense that the probability that Vn minus mu is greater than epsilon decreases as 2e to the minus 2n epsilon square. So it decreases exponentially in n. Very quickly you converge to the true mean value. So this is a Hofdings inequality. You may or may not have seen it depending on your background, but it's a standard inequality. You can read it in any textbook, in any probability textbook. So we won't prove it in interest of time, but this is an inequality you should know in this course. It just says that it basically quantifies how fast the average of n random variables converges to the mean, the rate of convergence, and shows it is exponential in n. Another way of interpreting this bound is that probability Vn is in mu minus epsilon to mu plus epsilon. Probability that this happens, let me not confuse the different terms. So probability Vn belongs to this interval, mu minus epsilon to mu plus epsilon, is very high. It says that it is in fact greater than 1 minus delta. And I don't have an equality here, I should have an inequality, of course. So where delta is 2e to the minus 2n epsilon square. So it says that Vn will be very close to mu. In fact, it will be between mu minus epsilon and mu plus epsilon with very high probability. In statistics, this right-hand side is called the confidence interval or confidence level, excuse me. And this quantity here is called the confidence interval. Okay. So it says that we are going to be very close to the mu, in the sense that with very high probability, we will be between mu minus epsilon and mu plus epsilon. We can also express epsilon in terms of delta. If we just invert this relationship, note that epsilon is 1 over 2n log 2 by delta. So what this is saying is, when we sketch Vn as a function of n, this is the mu that we have. Then we have we have two confidence intervals. This is mu plus epsilon and this is mu minus epsilon, where epsilon is given by this quantity. So if we fix delta to be, say, 0.01, then we have a 99% confidence level. Okay. Once we fix delta, we can compute the confidence interval as a function of n by using epsilon to be square root of 1 over 2n log 2 over delta. And for any given n, we can compute the confidence interval, and we can say that with very high probability, Vn is between these two limits. And this is an interpretation that is very useful in statistics when we try to estimate quantities. So before I move on, any questions? You can unmute your microphone and ask any questions you have. Just to be clear, are people still able to hear me properly? Can someone respond? Hello?
Yes, we can hear you. Hi.
Okay. So any questions at all from anyone? Is the speed too fast? Is it good? Okay. Since there is no feedback, I will continue on. At any point, if the audio is not clear or if there is any problems, just let me know so we can we can accordingly adjust. You know, this is first time I'm experimenting with an online delivery and using Zoom. So I am not. This is so. If there could be glitches. Okay, so I gave a simple example that I'm sure all of you have seen in some probability course beforehand, nothing fancy about it. But the question is, how is this connected to Pac Learning? How is this example connected to Pac Learning? Okay, let's explore that next. So let's consider, we had this whole framework of Pac Learning here, right? Where we have unknown function, we have the training data, and then we try to learn element of the hypothesis set H. So how is this related? So let's assume that the hypothesis H is selected before observing the training set. So it's a fixed hypothesis. It does not depend on the training data. We already decided beforehand, this is the model we want to use. If it is classification, we already decided which straight line we want to use as a classification boundary. So there is nothing really in order to learn here. Let's start with that very simple case. We can still define for this case the training error and the test error as before, and we want to find a relationship between them. Note that I'm using H instead of G now because G is typically what is learned after observing the training data. Here I'm considering the case of a fixed hypothesis. So we are not trying to learn anything at this point. But I want to find a relationship between E in and E out based on the example we just saw. So our goal is to find, we can compute E in because H is fixed, the training data set is given to us. So this can be computed. And we want to see how close is E out compared to E in. Okay, so let's try to connect this to the example we just studied. Let's for simplicity define mu to be the probability that y is not equal to hx. This is the quantity that we want to estimate. Okay, let's define zi to be e of yi and h of xi, and we'll consider classification. So this is 1 if yi is not equal to h of xi, and 0 if yi equals h of xi. Okay, so this is the function. So we can write E in to be 1 over n, I going from 1 to n zi. Okay. Also note that ZIs are IID Bernoulli mu. All the random variables are IID and they are Bernoulli mu. Okay. So this setting now looks very similar to the example we had before. This is nothing but our Vn. And so if we want to compute the probability that E in, and I'll put H here just to emphasize it's a function of the hypothesis that we have selected, minus E out of H is greater than epsilon, then this is basically our Vn, this is our mu, and so we can use Hofding to show that this is less than 2 e to the minus 2n epsilon square. And so immediately that example applies. To define this to be delta as before, then we have the same story that with probability greater than 1 minus delta, what we have is that E in of H minus E out of H is greater than epsilon, which is square root of 1 over 2n. So this is just repeating the example we just did. Okay. Now, because we have an absolute value, we have that E in minus E out is going to be, or this should be less than, beg your pardon. E in minus E out is less than epsilon, and E out minus E in is less than epsilon. Now, in practice, what we want is an upper bound on the test error. So from this, we just take one side of the equality or inequality, and what we have is that E out of H is less than E in of H plus square root of 1 over 2n log 2 by delta. So this says that if our training error was small, if E in of H, which we can compute, is small, then with high probability, our test error will also be small. It will be less than the training error plus a term that decreases as 1 over 2n log 2 over delta. So delta, remember, is our confidence interval. So delta is, if we want 99% confidence interval, the confidence level, then delta will be like 0.01. So this is some fixed constant. And it says that the test error will be smaller than training error plus a term that decreases as 1 over square root of n. So n is the number of samples. So the more samples we have, the more confident we will be. So this sounds good, but there is an important catch here. The catch here is that the hypothesis H was assumed to be fixed. There is nothing really to learn here. We assume that the hypothesis H is fixed and it was selected before observing the training set. Now in practice, this is never the case. We always are given data we want to learn. So remember how we had it? We have the training set D, and that goes into the learning algorithm A, where we have the hypothesis class, hypothesis set H, and we get our output hypothesis. Now, what we were currently did is we bypass this entire step. We said we are not going to, our learning algorithm is a trivial one. It's not going to do any learning. It's going to ignore the training set, just pick one element from H, whatever it decides upfront, and use that. Then it computes the training error. And if the training error happens to be small, we know that the test error is small. But in practice, why should the training error be small? We have not done any learning, right? We have to do learning on the training set in order to get the output hypothesis G. So because of that, we will have to sort of revisit this and redo the sort of the analysis. So are there any questions at this point about the example that we just did? Okay, so let me take a 5 to 10 minute break and we will continue our discussion. If you have any questions, I will stop sharing right now. If you have any questions, you can ask me either through microphone or through chat. So there is a question on chat if you are going to post the recording. Yes, I hope everything is getting recorded properly. And assuming it does, I will post the whole recording. So you will be able to go over it at your own pace. You can always unmute and ask me any questions. And if anybody is auditing and wants to be added, you can always email me and I can add you.
Sorry, Professor, is there any TA for the course?
So far, no, I have not heard from the grad office about any TAs. I want to first check the level of enrollment in the course. I want to see how many students, because last year we started with more than 35 students, but there were less than 10 students in the end. So I just want to check the enrollment level and then we will know if we have the TAs. But if there are, then I will announce it. As of now, I don't, but hopefully there are, and then they can help you. Last year we had TAs.
Understand, thank you.
Hi, Professor.
Yeah?
Are we gonna have any tutorials for this class?
No, just lectures and Piazza discussion.
Okay, thank you.
Hello, Professor. So I wonder project. Can you please mention about project more?
So
Is it gonna be like
50% of the
individual
grade.
or
Basically, I expect you to survey 1 or 2 papers related to the topics covered in the course, and read them and summarize them, provide some critical discussion. If you can try to build upon the ideas, that is fantastic, but it's not entirely needed. But I want you to look at least 2 papers. Yeah, 2 papers is a good number, and then sort of read them and understand them, summarize the results, provide some critical discussion. That's what you will be graded on. I will provide a rubric of the grading scheme as we in a few weeks. But that's the plan.
Okay, thank you.
Okay, so we'll resume now, if everyone is okay. So before the break, we introduced the framework of Pac Learning. And we basically, how do I make this full screen? And we basically, can everyone see the screen and everything is okay? There was another.
Yeah, it
Yes.
is.
Okay, thank you. So before the break, we introduced the framework of Pac Learning, and we showed that if in a very special case, if we have a trivial learning algorithm where we do not learn based on the training set, but fix the hypothesis, we can provide a guarantee between the test error and the training error. The training error, if the training error is small, the test error will be small with high probability. Using this particular approach of confidence intervals. Now what we want to do is we want to add learning to it. So what we will do is we will we will sort of assume for now that our hypothesis set H has finitely many elements. Okay, so we'll assume that H is of the form H1, H2 up to HM. So there are M possibilities that we can, so this could be like M different decision rules, for example, if we are considering, say, linear classification. Okay, but we cannot freely choose any line. There are only fixed number of lines and we can choose one out of them in this particular case. Then we will extend later on to the case when we can select any decision boundary and so on. But right now we are assuming that there are M possible candidate hypotheses. G is selected from H. So it has to be an element of H, but it can be freely selected after observing the training set D. Okay, so we can select D after observing. So we can select G to be H1 or H2 or HM, but we have the freedom of selecting it after we see the training set D. In the previous case, we fixed G to be H1 or H2 before observing D, and that was not very interesting. This is slightly more interesting because we can see we fix H to take M different values, and then we reveal the training set D, and then we select the hypothesis G. Okay, so, and we want to now get a guarantee between E out and E in for this particular case. Now we can again proceed in the same way. We can define E in of G to be 1 over n, summation of I going from 1 to n, E of yi and G of xi. and E out of G to be the probability that Y is not equal to Gx. So we can define this to be Zi. So Zi is 1, say if Yi is not equal to G of Xi, and 0 if Yi equals G of. And now this looks very much like Vn, right? So En of G is 1 over n summation of I going from 1 to n Zi. And so it is tempting to say that we can still say that the probability En of G minus E out of G, we want to somehow bound this, okay? And remember, this is like the summation of n Bernoulli random variables. So each Zi is Bernoulli. And this is the mean. So it's tempting to say that we could use Hofding. But the problem here is that the Hofding inequality cannot be applied. Because if you look at it carefully, what is happening is that this G is selected after observing x1, y1 up to xn, yn, after observing the training set. So when you look at the Zi, the G here depends on x1 to xn. Okay? So as a result of that, Zi's are no longer IID because G is a function of all the training points. And as a result of that, the Zi's are no longer going to be IID. And hence, Hofding cannot be used. So we cannot say that probability E in of G minus E out of G greater than epsilon is less than 2 e to the minus 2n epsilon square. This does not work. Okay, this is not true because Hofding cannot be used because E in of G is not a sum of IID random variables anymore. So as a result of that, this particular bound does not immediately apply. Okay? However, there is a simple fix to this. And the fix comes from a technique known as union bound. So what are we doing here? Let's define, for simplicity, delta of G to be E in of G minus E out of G. Okay, the absolute value of this difference. This is also known as the generalization error in the literature. Okay. Let's define delta of HI to be E in of HI minus E out of HI. Okay. This is the generalization error for the ith hypothesis for each HI in the set H. Now the claim that we have is that if we consider the event that delta of G is greater than or equal to epsilon. So this is an event where our training set is a bad set. In this set, E in of G is going to be small, but E out of G is large. So the difference between them is greater than epsilon. So we have a bad training set so that the training error looks small, but the test error is large. The claim is that this event happens only if one of the original hypothesis is bad. So delta of HI, at least one of the same training set should be bad either for H1 or for H2 or for H3 up to HM. One of the hypotheses should be a bad hypothesis. If all the hypotheses are good hypotheses, so that its training set is good for all the hypotheses, so delta of HI is less than epsilon, there is no way that this left-hand side error will happen, that delta of G will be greater than epsilon. So this is a clear fact, and this simply follows since G is an element of H, has H1, H2 up to HM. Okay? So G is either H1 or it is H2 or up to HM. It cannot take any other values. As a result of that, if for each I, delta of HI is less than epsilon, then delta of G by definition will be less than epsilon. So if a training set is bad for G, it has to be bad for at least one of the hypotheses. It can be bad for many of them, that is fine, but it has to be bad for at least one of them. If it is good for all of them, it by definition has to be good for G. So that we cannot have that generalization error is bad for G if it is good for all the hypotheses H1 to HM. Okay, so this is a clear fact. If you think about this for a bit, this will become obvious, but you need to sort of convince yourself. But it's a very simple observation. As a result of this, probability that delta of G is greater than epsilon is less than probability of union of I going from 1 to M. Delta of HI is greater than epsilon. This just comes from the inclusion principle. Since this event is the left-hand event is included in the right-hand event, the probability of the left-hand event is less than the probability of the right-hand event. Now we can apply union bound to this. And so this means that this is less than the summation of I going from 1 to M. Probability of delta of HI is greater than epsilon. Okay. So delta of HI is probability that E in of HI minus E out of HI greater than epsilon. And for each HI, it's a fixed hypothesis. This was selected before observing the training set. H was fixed, right? So for each of them, we can apply the usual Hofdings. So this is less than 2m e to the minus 2n epsilon square. So what we have shown is that if we look at probability E in of G minus E out of G greater than epsilon, this is less than 2m e to the minus 2n epsilon square. This is what we have shown. So if G was a fixed hypothesis, we would not have this factor of m. This is the extra penalty that we pay due to adaptivity. Since we are allowing G to be dependent on the training set D, we have to pay this additional factor of m in our penalty in the upper bound. So again, after that, everything is standard. If we set this to delta, then we can show that with probability greater than 1 minus delta, we have that E out of G is less than E in of G plus now square root of 1 over 2n log 2m by delta. Okay. So the additional penalty comes from is a factor of m. So when we actually do learning, the test error will be smaller than the training error plus a term now that increases as log of 2m by delta. Okay. So it still decreases with the number of training samples as 1 over 2n. So we still have the 1 over root n decrease. But because of adaptivity, we have a higher constant. We have log of 2m instead of log of 2 before. So this is basically how we account for adaptivity. So this looks good. However, there is a big problem. In practice, in most practical applications, we have m equals infinity. In fact, the number of hypotheses is not even countable. If we just consider the simple case of linear classification, you want to draw any arbitrary line as a classifier. You do not want to restrict to like say 10 different classifiers, right? Which is what this case is. So m is going to be infinite if you can draw any arbitrary line. And if you do that, then this bound becomes a trivial bound. It just says E out is less than infinity. So this is again not very useful in practical systems. You want to have tighter, a much better bound than what this bound gives you. Okay, so we will fix this. So the key idea that we will use to fix this is to strengthen the union bound by replacing H with a term known by replacing M, not H, we'll make it M, effective number of hypotheses. Okay, so we will try to now further improve upon the union bound. In order to do that, we have to introduce a concept called a dichotomy vector. So let x1, x2 up to xn be given points. Then the dichotomy vector of any hypothesis H is the vector H of x1, H of x2 up to H of xn. So it's the evaluation of the hypothesis on the endpoints. Now we will focus throughout on binary linear classification from now on. So our labels will take values plus and minus 1 for simplicity. And so H will be a function from Rd to the set -1 to +1. As a result, the dichotomy vector will be a vector of this form. Each entry will be +1 or -1, and there will be n of them. So it will be a vector of length n, each element of which is either +1 or -1. Now, the set, the dichotomy set of H, denoted by H of x1 to xn, is basically the collection of dichotomy vectors for each H in the set H. Okay, so it's basically just enumeration of all points of all hypotheses in the set H. So to think about it, let's consider the case when n is 3 and we are in 2 dimensions, and suppose we have 3 points like this. Okay, then what we do is we compute H of x1, H of x2, H of x3. So you can think of putting a paper on this plane, on this 2-dimensional plane, puncturing holes at where x1, x2, and x3 are, and then evaluating each hypothesis in the set H at these 3 points, and enumerating the entire, all the possible vectors that you get. That is what the dichotomy set H of x1 to xn is. Now, clearly, you can easily convince yourself the size of H is less than 2 to the n, because there are at most, each element can be +1 or -1, and there are at most 2 to the n such vectors. But the point is that in practice, H of x1 to xn will be much smaller. It won't be of the order of 2 to the n. In fact, it won't increase exponentially in n. It will increase polynomially in n. And this is what will make learning possible and allow us to characterize the effective number of hypotheses. So the point is that it's not like, for most practical hypothesis classes, we will not have all possible 2 to the n dichotomy vectors on endpoints. We will only have a small subset of them. And as a result of that, in fact, generalization and learning will be possible, and we will have a small number of effective number of hypotheses. Now we say that a hypothesis class H shatters x1, x2 up to xn if H is as diverse as possible on x1 to xn. That is, if you look at the size of H of x1 to xn, it is in fact equal to 2 to the n. In that case, we say that H shatters x1 to xn. Okay, so let's do an example. Let's consider binary linear classification, and let's consider the case of 2 dimensions. So data vector x has 2 points, has 2 elements, so it's an element in R2. Okay, and so what we are considering are hypothesis class like this. If you have, say, this is x1, this is x2 axis, any decision rule will be a straight line. So this will be of the form y sine of w0 plus w1 x1 plus w2 x2. On one side, you will have a label of +1. On the other side, you will have a label of -1. So this is the decision rules we do. We consider any arbitrary line. So this is a very large hypothesis class, infinite number of hypotheses, uncountably infinite. You can draw a straight line as you wish. And then one side of it is plus, the other side must be minus. So mathematically, this will be the sort of relation we have. Y is w sine of w0 plus w1 x1 plus w2 x2. Okay, this is the equation of a line, and you evaluate the sign to know whether you're on above the line or below the line. So this is our hypothesis class. Collection of all straight lines. Let's say that we have 3 points. So we have 3 data points like this. Okay, and the question is, what dichotomies are possible? Find the dichotomy set H of x1, x2, x3. Okay, so clearly you can, the question is which of these dichotomies are possible? Is plus 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 possible? Sure, you can draw maybe a line, perhaps like this, and say here you have a plus and here you have a minus. So that is definitely possible. Is a plus minus possible? So we want plus at x1 and x2 and minus at x3. Sure, you can have a line like this. Plus minus is possible. Is plus minus plus possible? Yeah, you can draw a line like this, or no, not like this, but maybe like this. So now x2 can be minus, this can be plus, and very quickly you can verify yourself that all the dichotomies are possible. Okay, and similarly, these are all can be realized by some decision rule. Okay, for these 3 points. As a result, in this case, H of x1, x2, x3 is 8. So H shatters x1, x2, x3. Now consider another case. Suppose that x1, x2, and x3 lie on a straight line. So there is some straight line that passes through x1, x2, x3. Now the question is, which dichotomies are possible? Let's write them. Okay. Plus, 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 is this possible? Sure, I can draw maybe a line like this and make this everything here plus. So this is possible. Plus, plus, minus, I can draw a line like this, make everything positive here, negative here. So this is possible. Plus, minus, plus, is this possible? This is one that is not possible actually, because you cannot draw a line such that you can have plus here and then minus at x2 and plus at x3. So this is not possible. Is minus plus plus possible? Yeah, sure. This a line like this will make you make minus here and plus here, makes it work. So you can see that all of these three dichotomies are possible. The plus plus plus, plus plus minus, and minus plus plus, but this one is not. And likewise, this one is not possible, and the other three are possible. So as a result of this, in this case, h of x1, x2, x3 is 6 and not 8. And in the first problem set, you will have a lot of practice studying how you can construct dichotomy vectors, how to compute when the hypothesis class shatters, and so on. Now let's consider the case when n is 4 instead of 3. So imagine you have 4 points like this. And the question is, which dichotomies are possible in this case? So let's write them down. There are 16 of them. Do this. Then I will, I guess, switch them. So plus, plus, minus, plus, this was remaining. Plus, 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 minus, minus, minus. No, that is done. So plus, plus, minus, plus, plus, minus, minus, plus. Then we need 2 more. Plus, plus. So systematic here. Plus, minus, plus, plus. And then plus, minus, minus, plus, and then the negative of these. So these are 8, and then the negative, and the ones where you have minus in the front, and then you repeat. Okay. Now you can, now the questions, which of these are possible? So you can try as an exercise all of them, and you will quickly see that the 2 that are not possible are the ones where you have one sign for x1 and x3 and an opposite sign for x2 and x4. So plus, minus, plus, and minus. Do I have that? Plus, minus. So I will let you check, and you can check, maybe I didn't write all this properly, but plus, minus, plus, minus, and minus, plus, minus, plus. These 2 are not possible. Yeah, I think I repeated this and this. That's why. So these 2 were repeated. So let me change it. This is the one, and minus, plus. So this is a dichotomy that is not possible. Because you cannot separate x2 and x4 have one sign and x1 and x3 have another sign. So these are all possible. You can check for yourself. But the last one is not possible. And likewise, I think I have, this should be all plus here. And minus plus, minus plus, this one. All the rest are going to be possible. Okay, so you can, in this case, what you can show is that the size of H, x1, x2, x3, x4 is going to be 14. So you cannot realize all 16 dichotomy vectors when there are 4 points. You can have at most 14 vectors. So this is the example of what the dichotomy set is for linear classification. The next definition is that of a growth function. Given a dichotomy set H, MH of n is the maximum of the size of x1 to xn, where we optimize over the placement of the endpoints. So we can decide how to place x1 to xn such that we maximize the size of the dichotomy set of H. That is the growth function MH of n. For linear classification, when n is 3, we saw that there were 2 cases. There was this case here, when there were 8 points possible, and then there were the collinear case when only 6 points were possible. So in this case, MH of n, when n is 3, is going to be 8, because there is one configuration of points where all 8 vectors are possible. When n is 4, no matter, and this is for 2 dimensions, no matter how we place the points, we only get 14 possibilities. So for 4 points, we never shatter the hypothesis class never shatters the 4 points. And the growth function is always less than 2 to the 4. It's always 14. Now the VC dimension. So that the next important concept is that of a VC dimension, known as Vapnik-Chervonenkis dimension. This is the name of the people who came up with this theory. It says the following: given H, let n be the largest integer such that MH of n is 2 to the n. So H shatters, there's some configuration of H n points that are shattered by H, but MH of n plus 1 is less than 2 to the n plus 1. So n plus 1 points cannot be shattered. Then the VC dimension of H is equal to n. So for linear classification, in 2 dimensions, we had that the VC dimension is equal to 3. More generally, you can show that in D dimensions, if you're doing linear classification in D dimensions, the VC dimension is actually D plus 1. In 2 dimensions, it is 3. In D dimensions, it is D plus 1. And so basically, VC dimension is one of the most fundamental quantities in machine learning. It will be on in statistical learning. And I will stop today's lecture here. Starting next lecture, which is already the video posted, you will derive a Pac Learning bound using the concept of VC dimension. So this is what we will be covering in the next lecture. So now I conclude our discussion today. Today's lecture was an introduction to Pac Learning, a basic derivation involving Hofdings inequality and finding the generalization error when we have finitely many hypotheses, and a brief introduction to VC dimension. To better understand this material, please read chapters 1 and 2 from the following book. It's called Learning from Data. It is by Yasser Abu Mustafa et al. Okay, so I'll stop here. I will take any questions you have, and we will continue next. So for next week, the lectures are already posted, so please see them beforehand. You can ask any questions about today's lecture or next week's lecture on Piazza discussion forum. And then next week when I start at 2 p.m., I will basically have an office hour where you would have seen the lecture, and I will do a short summary and I will answer any questions you have. So we can stop here. You can either hang out and ask me questions, or if you are done, you can sign off. Thank you very much.
Professor?
Yeah?
Will you upload this video as well?
I will upload. Assuming this is all properly recorded, I will upload it.
Okay, thanks. And
I will
do you have
upload
any...
the notes and the recorded lecture. If not, I will record it and upload it.
And do we have any homework for next week?
Do I have any what?
Do we have any homework for next week?
There are two homeworks. They are both posted on Quarkus, two problem sets. So I'm going back to the course grading scheme. This is the course grading scheme I discussed. There is 10% for participation based on your discussion in Piazza, your interaction during the lectures. 20% for problem set 1, 20% for problem set 2. Both problem sets have been posted. You can actually start problem set 1 now if you wish. Some of the top material will already be there. Problem set 1 is essentially taken from the reference I gave you, Learning from Data. So it's a good idea to read it and start. It is due sometime early October. So you have a few weeks. And then problem set 2 is due sometime in mid-November, I believe. So both problem sets are posted. All the lecture material is posted starting next week. So you can essentially do the course based on your pace. If you want to start doing it as soon as possible, that is perfectly fine. So you can pace it. However, for the weekly basis, I will be discussing the material only for that week.
Okay, thank you.
Sorry, Professor, today's lecture is finished?
Yes, today's I am pretty much done now, because the thing is I end up going fast because there's no interaction, right? I cannot pause and ask too many questions. So for today, I think we have covered a fair bit of material. If there are any questions, I can basically take them now. I can do 1 or 2 additional examples if you wish, but in terms of, if you want, I can do 1 or 2 examples on this growth function and dichotomy set if you wish. Are people interested in that?
Sure.
Okay, so I will let you do it so that to make sure as you how much you understand. Let's consider the following hypothesis class: y equals sine of x minus a. So we are in 1 dimension. Our data vector, the input is a scalar function. X is a real number, right? So it's at some point here. A is a fixed threshold. So this is, we call this HA of X. Okay. So there is some number on this real line. To the right of it, y will be +1. To the left of it, y will be -1. Okay. Now we are given n points. So we are given x1, x2 up to xn. Okay. Now what is the hypothesis class? H is the collection of functions HA of x where A is a real number. So all we are allowed to do is change the location of A. If we put A here, then the function output function will look like this, shown in this example. If I move A to the right, then basically I'm making y equals 1 to be further to the right and y equals -1 to be the rest of the region, and so on, right? And what I want to do is basically compute for this endpoints h of x1 to xn. So can anyone tell me what it is? What is the dichotomy set here? How will it look like? So you can go through the definitions we had and you can look through them, and I want to see who can answer this question.
Professor, could you repeat the question for a second? I'm not
So
quite
this is
sure I
what you have to
understood it.
compute. So basically you have, this is the hypothesis class, right? It's a set of all basically functions where to the right of this point A, the label is +1, to the left of it, the label is -1. Now you're given endpoints x1 to xn as shown in the figure. And you want to compute a dichotomy set, h of x1 to xn.
Is it 2?
No, it will be, it depends on n. It's a function of n, right?
Yeah, oh yeah, you're right.
X equals less than A on one side.
That's right. So the way you will start it is you have x1, x2 to xn, and you want to know what labels are possible at these points. You have a freedom of selecting A anywhere on this line. If you start here, if you pick A to be here, then everything to the right will be a plus and everything to the left will be a minus. So in that case, the dichotomy vector you get will be plus, 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 and plus. So this is one dichotomy vector that is possible. Now, if I move A to the right, so now if I, instead of this value of A, I can move A, so it is here between x1 and x2. So now everything here will be labeled as plus and everything here will be labeled as minus, right? So now the other dichotomy vector I have is minus, plus, plus, and so on. Then I can move it, so it is further. Let's say I also write x3 for simplicity. Then I can move A somewhere between x2 and x3. And everything here will be minus, everything here will be a plus. Now I have minus, minus, and so on. So do people see a pattern? Can anyone tell me what the hypothesis, what this is, and what the growth function is for this set?
Would it just be like n or n plus 1?
It is actually n plus 1. That's right. So
yeah,
basically
because
these
you
are
have everything.
right, exactly. So these are all the dichotomies that will be possible. So everything on one side has to be minus, on the other side has to be plus. So based on this, you can see that this is the growth function in this case. Now to compute the VC dimension, we want to compute the VC dimension of H. What we will do is we will find the value of n for which mh of n is equal to 2 to the n, right? This is the largest n for which this is possible is the VC dimension. So let's try to sketch mh of n here. Okay, when n is 1, so it's in this case a linear function. So mh of 1 is 2, mh of 2 is 3. It's a straight line like this. Okay, now we want to find the largest n for which we have that mh of n is 2 to the n. If we sketch, like, let's consider the line, let's consider the function g of n is 2 to the n. So at 1 it's 2, at 2 it is 4, at 3 it is 8, and so the g of n looks like this, right? So the only point where we have this equality is when n is 1. As a result, the VC dimension of this hypothesis class is 1. It's the only point at which you have that Gn intersects the growth function. What we will see next class is that there is a very interesting bound we can have on the growth function. We can show that the growth function is always upper bounded by the VC increases polynomially in n. It is upper bounded by n to the dVC of h plus 1. So this is the VC dimension, and it increases polynomially in n. Okay. So up to a certain point, up to a VC dimension, you will have the exponential decrease. But after that, the growth function will always increase polynomially in n. It will not increase exponentially in n. This is a very important result that we will see in the next lecture. And this will allow learning to be possible for the case of infinitely many hypotheses. Any questions? So I encourage you to go through the notes. I know it was a little fast. It is hard to have interaction with the class, at least for me, if I don't have eye contact and see students in person. So what I do is I just go through the lecture material. If I had to cover this in a normal lecture, it would be more than 2 hours. But when we have a Skype thing, I try to just go through the lectures. I encourage you to go through the video later on and again, see if you have any questions, and you can ask them about this lecture or the next lecture. I will hang out for a few minutes to have any, if there are any more questions. Otherwise, we are done for today's lecture. You can sign off, and I will upload the video and send you sort of some instructions after the lecture.
Go ahead.
Oh, sorry, I was just gonna ask, is there an edition of the textbook, or is there just like one version if we wanted to get a copy?
I think there's only one version.
Okay, cool.
And this is not really a textbook. This will only be used for the first 3-4 lectures.
Okay.
What the final project would be like?
The what?
The final project?
You can basically read 2 research papers, like in sort of top conferences, summarize them and try to give some comparison between them. You can critique them, try to sort of do some experiments. It's really open-ended as to what your interests are, because this course is really designed for students who are like experts in communication systems and who really want to understand statistical learning. So a research project will be a natural fit for them. They would know what they are really doing, right? So that is the idea. So it's open-ended. You can choose what you want to do.
And the papers
I
are
will also
basically.
add that I will be offering this course in future. So if when there is in-person lectures, I think it will be easier. So if you have an opportunity to take it next year, I would encourage you to try it then. I don't find this to be a very ideal platform, to be honest. But if you have to take it this year, it is understandable. So.
And the papers we'll be reading, it's going to be ML related or?
It could be two related papers on a related topic.
But if I understand correctly, statistical learning is basically kind of machine learning, right?
It's basically some theory. Now, as I said, there are many courses in this university. Each of them has a different treatment of the subject under the title statistical learning, right? So CSC 2532, STA 314, these are like different courses on statistical learning. The material I am teaching is sort of more aligned to the interests we have more in the communication side. So how are information theoretic bounds useful for generalization? What are minimax lower bounds? How graphical models can be used, and so on. So this is a set of topics I have selected for this course. It's by no means a universal choice. If you are interested in these topics, you're welcome to take this course, or you might find some other courses more useful to your interests.
Okay, thank you.
Anybody has any more questions? All right, then we'll end the course now, and I'll see you on Piazza if you have any questions, and see you next Monday at 2 p.m. Sorry for the delay today. We will continue next week.